Fantastic, Leon. So as you guys know, computational design is such a broad topic, and most times it leaves students and even seasoned professionals confused. Or at best, it gets used early on in the design, either, programmatic explorations or form finding. And honestly, computational design is not a silver bullet, right? It's a methodology that's applicable at every phase of a project's life cycle and beneficial to any roles within the A&C industry. And in light of CoAD's mission, we'll be exploring the application of computational design methodologies in technical design and digital fabrication with some amazing guests who I'm so excited to introduce, some of whom I've worked with. But for us to probably explore this topic, we have two parts to the event: a presentation and a panel discussion. So for the presentation, again, we ask that you post all questions using the Zoom Q&A feature, and feel free to vote certain questions up so that they get answered. So to kick things off with the presentation, allow me to introduce my buddy Gustav Fagerström, a registered architect and digital practice leader with Walter P. Moore Engineering, New York, where he leads the computational modeling for structural and facade engineering. Having global experience at all stages of the project lifecycle in over 10 different countries, he specializes in design computation at the intersection of architecture, engineering, and computer science. His work has been exhibited all over the world, in Europe, America, Asia. He's presented at Autodesk University, Acadia, Fabricate. He's a part of the Smart Geometry conference. He's also faculty at Pratt Institute and consultant and pen design. So for those who don't know, he's actually some musician. I don't know if he wanted me to say that, but yes, he is. So Gustav, take it away.
Thank you, Zubi. I play. There's a reason why I didn't make music my profession. So most people never get to hear it, but I enjoy it. Thank you so much for the invite. This is really great. I'm very happy to be here with this lineup and this great kind of set of lectures that you guys have been putting on in this wonderful setting of Code Detroit. This is really great. I will be speaking for, I think this will take about 45 minutes, but we'll see exactly how long that lasts. And I think also, Lauren, I'll pause maybe once or twice. If questions are coming in, we can take them as they come. I'm not great at multitasking though in that way, so I won't be able to read them. But if you think that there is anything, important to catch on the fly, then I'll pause and see if there's anything. Otherwise, we'll take it at the end, I suppose. Okay, so let's see if the mysterious screen share works and the mysterious presentation view. And not sharing that, maybe. How does that look? Yeah, good, okay. Okay, so I work for a company called Walter P. Moore. We are an engineering firm that has its origins in Houston, Texas, and who has been doing civil and structural engineering for a long time, actually since the 1930s. In the last 10 years, give or take, the division of facade engineering was born. And that's the one that I am specifically part of in the New York office. And in the last 5-6 years, we've done a lot of really interesting. Walter P. Moore itself is known for long span structures and retractable roofs, large scale projects in general. And when facade engineering kind of came about in a very sort of well-rounded and experienced engineering practice, it kind of took off with the hit the ground running, so to speak, and has done a lot of work in the relatively short time that our group has been in existence. And I'm very happy to be part of that almost from the beginning and from the very beginning in New York, and look forward to where we take that next. And obviously we put a very heavy focus on computational design systems, and on following through with that. This is kind of the theme of today, like following through with that from very early stages, option studies, where everything is pretty fluid, and all the way to the construction stage. And we actually have a quite frequent involvement also with fabrication modeling, where we take projects and we do the modeling for the fabricators and engineering for the contractors. So I'll be talking today about a project that was a little bit more of a traditional design bid build type delivery, but with still some early contractor involvement. I'll get to that a little bit later, why that is important to this presentation. Here you can see, just on a general note, here you can see kind of our company, where we do most of our work. It's a lot of it is in continental US, but we do work elsewhere in the world, and have offices also in a couple of other countries like Canada, Panama, and India more specifically. Some kind of projects of note before we go into the specific one I'm going to talk about here is, from top left, you got the Jacksonville Jaguars practice field in Jacksonville, Florida. Then over to the right from there is the Lucas Museum of Narrative Arts in Los Angeles, California. Here we have the Academy of Motion Pictures Arts and Sciences in California as well. Over to the right again is the Allianz Arena, which is the field for the Minnesota United. Here is the gatehouse for the Golden State Warriors arena that we'll be talking about today. This here is at the Angle Lake, SeaTac, and this is actually a rendering that is old, and I don't want to talk about it because the project is now built. It's the one we're going to talk about today. Here's the Rams Stadium, again, recently inaugurated in LA. Here again, today's project. This is the new terminal for the New Orleans Airport, the Fagerstrӧm Airport in New Orleans, Louisiana. And this finally is the so-called Mars Pavilion that was built out of robotically fabric-formed concrete for an event that Amazon held a couple of years ago. So there's a lot of different scales and kind of typologies of buildings that we get involved in, and today we'll specifically be talking about the kind of deep involvement we have in sports, and that all started actually with this here building that you might recognize. This is the Astrodome from 1965. This was done without any computational design tools, and still was done, of course, and is still going strong. And of course, being involved in kind of complex, long span architecture and structural engineering so early on, our team has had a very long tradition in kind of figuring out how to work together with architects, with other engineering consultancy disciplines, and how to sort of deliver difficult projects, even with fairly complex setups, and just in terms of like how the design team is structured, for instance. And I'll get to that in a second, on the note, in fact, of working together. So the case study of today is the Chase Center. Its official name. It's the Golden State Warriors home turf in the San Francisco Mission Bay. This is an area that used to be called the Dog Patch. And as some of you might know, the Warriors were a team in Oakland on the other side of the water from this photo, until they somewhat controversially, for many people, were moved into San Francisco proper. That is an issue that I take no position on, but that was something that many people cared about quite deeply. And hopefully the existence of a top class home field can offset some of the sense of that, whether they should have moved or not, depending on where you stand in that question. And the reason, I think one of the reasons why this has become a really successful project is that it's part of a larger urban intervention here. So if you can see my mouse on the screen, it's sort of all of this here is about, if I'm not mistaken, about 500,000 square feet of mixed-use development with the arena at its center. If you have worked on sports projects yourselves, you might know, be familiar with that some of them tend to kind of land a little bit like an alien presence in the city and not really relate much to its surroundings. And I think that the team that did the master plan here, they did a really good job at avoiding that and to insert it in a urban context where it sort of makes sense and where it interacts with its surroundings, and it creates, you know, a very successful, in my opinion, public space, which has been very well received and well visited. So this was completed in September, I think, of let me think now, September 2019, and I had the good fortune to visit once before traveling became difficult, as you're all familiar with. It's an 18,000 seat arena. And it also has a wealth of different kind of concerts and other public performances, which are supposedly great. I have not had the chance to actually see something in there, so that's on my to-do list still. So the very origins of this project were with a delivery method which is fairly common, especially here in the US, and I'm sure that many of you are familiar with it, which is the one in which there is a design architect, there is an executive architect, and then there's a set of consultants. In this case, the design architect is a firm called Manica, who are based in Kansas City, and they are very experienced and well-versed in sports projects. And then on the executive architect, the architect of record side, is a firm from Houston called Kendall Heaton Associates, who are also very experienced in delivering and executing projects and being the architect of record. However, when two firms with that sort of specialization need to take a project from the very early stages all the way to construction, especially in the kind of specialized building design systems, for instance, the facade system, there is a need for kind of a gap to be bridged, if you will. And that's where Walter P. Moore sat in this project. So our scope was between an architectural design intent and a set of bid construction drawings, was our task then to formulate and devise enclosure systems, do the enclosure engineering, geometric rationalization, discretization, and detailing, delivering that in the form of 3D models, both for enclosure and the secondary structure that holds up the enclosure, as well as a set of typical details. And of course, reporting the loads imposed on the primary structure from our systems. So I'll get to all of that, and specifically this will be about the piece that has to do with geometric rationalization and discretization, and also a fair bit about how the kind of quirks of how this product was delivered because of a series of different factors, really. So when we talk about rationalization, I'm sure that if you are geometry nerds like me, then you will have heard this, you will have worked with this, you will have undertaken exercises in the interest of sort of rationalizing things, and yet maybe it's a little bit hard to actually exactly pinpoint what it means to rationalize something for construction in this case. So we did a kind of musing on this a few years ago in a white paper that we wrote, talking about what it might mean to rationalize something in architecture, engineering, and construction. So as you might remember from math class, this is the mathematical definition of a rational number, where Q is not equal to 0. Now, rationalization then in geometry is actually a little bit counterintuitive, right? Because, for instance, the geometry that we often deal with and that we often find ourselves having to quote unquote rationalize is, in fact, strictly speaking, rational. NURBS, as you will probably be familiar with, means non-uniform rational B-spline, and that's because the NURBS geometry is, from a mathematical and computational geometry point of view, rational. So surfaces and curves are mathematically rational. However, that doesn't necessarily lead to a construction rationale. And that is maybe what we're after when we're trying to, again, quote unquote, rationalize something in a construction sense. So with rationalization being in a way kind of jargon in AEC, without a really universally established meaning, we have attempted to define it for ourselves, meaning inside of our computational design kind of expertise within our firm, not necessarily claiming to have defined it for the Oxford Dictionary, but certainly for ourselves, it's useful to put some precise meanings to terms that we use. So in the case study of this project, the Golden State Warriors Arena, there is you might think of it as two different levels of rationalization, where if you look at the left side here of this slide, the level 1 so-called rationalization is a large scale one, which aims to describe overall building geometric entities with various basic geometric equations, those that can be kind of, that are the simple parametric ones with lines, circles, ellipses, planes, and spheres, etc. And then as you zoom in, as you go down in scale into kind of more actual architectural assemblies and components that are like physical pieces of stuff, then the level 2 so-called rationalization comes into place, where the overall global geometry, the one seen on the left here under level 1, will be divided into discrete, in this case, planar elements with one-dimensional edges. So that is, a roundabout way of saying discretizing or tessellating or panelizing, whatever it is, depending on what kind of project you're working on. So in this particular case, it was about making flat, four-sided sheets, which are eventually going to be made out of metal and become a metal panel rain screen. And so at the start of that exercise, we have this. This is the surface model. There is more resolution to this, but this is the sort of global geometry that is given to us and that represents the front of cladding from kind of the design intent. And this, I think I'll get to that a little bit later. This obviously has undergone much work before it even gets to this point. But the point of the discussion here is that this needs to become this, and most of the work to go between those two stages of existence were, I should say, because the building has been built within Wolfe P. Moore's facade team's scope of work. So if we zoom in a little bit and look at what's actually the kind of architectural system here at play, this is if you look at the exploded axonometric, you see to the back there are the primary structural columns who are engineered by somebody else. We did not do that. So our system comes into play at that interface, where these struts here that are, if you see the double triangle here, creates a moment connection, so that this top horizontal tube here, which was known as the hoop, becomes a moment stiff gravity connection. So that's where all the self weight of the whole system is taken up and goes back via these struts here into the primary system. Then the lower end of the panels are pinned. So these here, it's a little bit hard to see in this view, but you'll see that later on the mock-up picture. So these struts here are pinned so that they, whenever the wind blows, the lateral forces that affect the building, they get transferred back here, but any self-weight is taken up, including the weight of this. The lower hoop is taken up by these hangers and goes back through this hoop and back through these gravity connections here. So this is basically a rain screen, where back here you see those are the cold form studs that are at the level of the slab edges, which is then where the sheathing and the waterproofing and the insulation will be attached. So the kind of assembly logic of this is like a curtain wall. If you're familiar with how those work, they are usually top hung. So you have your gravity connection at the top, and then you have a lateral pin only at the bottom. And the exact same thing goes here, except that the weather barrier is further back, like in a rain screen. And so this is basically the, you see the section here to the left. There are these sort of different kind of steps in and out so that we can maintain flat mega panels always. I'll get back to that as well, which is quite important. And as the fabricators here in the room will know too, that makes their life a whole lot easier. The sort of primitive version here is basically you have the dashed line, which is your climate barrier, and the blue kind of kinked line there is your visual skin that's seen from the outside in a complex shape. In the middle here, those are very simple, those are parallel, and then what we ended up doing so they can actually be split into manageable parts that can be assembled, transported, and installed. This is actually what comes out. And similarly, in terms of like conceptual geometric studies before anything actually sort of takes very final form, we did dozens and dozens of fairly quick hits in the earlier stages of different global area studies, like what would happen if you depending on the different offsets between structure and facade, how does that affect the square footage of the surface area of the facade, which is quite impactful to budget when you're dealing with these sort of surface areas involved in kind of big buildings like this. So you see this would then lead to kind of early stage costing, which can be roughly compared then to what the kind of the general contractor has put forward in their work towards a GMP. Now we don't get into costing proper, of course, because then that is usually a good deed that doesn't go unpunished, but it's nice sometimes to be able to keep track of this stuff just even for internal purposes and kind of sanity checks every now and then. I'm going to skip this in the interest of time. That too, this is more, deep dive into what the engineering of the secondary system does, and I think we can skip past that. So these are some vignettes in sort of early submissions just to show assembly logic of the secondary structure in a drawing format. Now we get to the rationalization. So here you have the different actual pieces that were defined based on that Rhino skin geometry that we were given, and these are called things like drums and ribbons and ATW means atrium west, ATE means atrium east. So we came up with this fixed length delimited naming scheme, which again, for computational purposes, you all know that it's pretty nifty to be able to always know what's on a certain position in a string, for instance, when you're querying something. So that was the sort of philosophy behind here, that you have a 3 plus 1 or 3 plus 2 or 3 plus 3 sometimes nomenclature, where the hyphen is the one that divides the kind of category from the specific position. Makes it a lot easier when you crunch the data later on. This is the level 1 rationalization, where we're deciding what is a discrete abstract piece of global setting out geometry, you might say, and how is that then defined? And the reason we're embarking on this exercise at this point in time, this is about halfway through DD, if I'm not mistaken, is that because of contractual reasons, there's a sort of back and forth where sometimes this project is supposed to be delivered in 3D. So we have actual 3D model based procurement. And then that goes away for contractual reasons that we usually have very little control over, and becomes a paper-based flat delivery, so to speak. And that happened a couple of times actually, back and forth. And it has, if you've been involved in it, you know that it has to do with liability and the way that we kind of still, as an industry, haven't really figured out how to write proper contracts from either side, so that everyone can feel that they're conveying what they want to, no more nor less, when they hand off a 3D model, or for that matter, just preparing it to sort of minimize their own staying up at night worrying about it, and worse. So that's I think an ongoing, and I'm happy to talk about that later if someone vehemently disagrees with me. But I think it's on all of us to get better at this. And I don't think we're at all there yet, but in this case, it went back and forth again, and eventually became a paper-based delivery, which is why all of this needs to happen, so that this can basically be delivered in a traditional design bid build sense where, somewhat simplified, we hand up a stack of paper, and someone has to interpret that stack of paper without any contact with us, right? That's the sort of extreme form of it. So this is the attempt to give this to someone on the contractor side who can basically pick it up and just build it from the instructions in the drawing set. So for that reason, everything is dumbed down, if you will, or rationalized, if you prefer that, into, I stand by both of those definitions. They're into primitive geometric shapes that represent architectural entities. So here you have an ellipse, which in this case represents the top edge of a specific drum of this global geometry. So an ellipse has a long and a short radius and a center point and a plane that it lives in, which is all you need to really define that ellipse. And then once you have those points in the plane and the two radii, the minor and the major radius, then you know what that ellipse is. And the other information, of course, you need in order to figure out what this blue ribbon here looks like is that you need to know where on the ellipse does it start, where on the ellipse does it stop, and then there's another ellipse that in this case, in a corresponding way defines its lower edge, and with a start and stopping point. And then those two sort of subcurves from these two ellipses are then, they become the edge curves for a ruled surface, and that becomes the definition of this particular piece of rationalization level 1 geometry. And then that goes on into slightly more intricate ways sometimes. For instance, here, because of the architectural kind of situation, this is an undercut, which is then achieved, which is in a non, it's neither parallel to one of the ellipses, nor is it in the direction of the plank lines of the surface. So this becomes one of those strange NURBS curves that changes radius continuously. But you can describe it by undercutting, in this case, the ruled surface with a plane that has a certain equation to itself, so that you don't actually really have to care what the dashed red line is. You just know that it's whatever is the product of the intersection of the plane and the ruled surface. And so that is what comes out of that, right? And then from there, if you kind of, if you extrapolate what I just showed into all of those shapes that were in the colored overview diagram before, then that goes into the level 2 rationalization from this diagram that you might remember. More specifically, these are mega panels of usually between 8 and 10 metal panels that are in themselves 8 feet wide by 3 feet tall. So when they are pre-assembled into mega panel kind of structures, they're about between 24 and 30 feet tall by 8 feet wide. So that sort of, and that is a flat plane, right? Each of these is a planar object, which when you are analyzing a curved shape like this, if for architectural reasons of architectural design intent, your panel joints can't necessarily always trace the plank lines of the ruled surfaces, then you get either curvature in your panels, which you kind of don't want, because then you're going to have to start curving your mullions and your metal sheets and whatnot. So you either do that, or you do a study in which one of the 4 corners, I mean, all 3 corners can always lie on a plane, right? But the 4th corner, whichever it may be, is going to poke out or in. I'm sure you've all done this type of exercise, and that's a pretty easy study to do. What's not so easy is to convince a client whether something which is poking out by 7/16 of an inch and which is 50 feet up in the air is actually visible or not. Luckily, I'm jumping the gun here a little bit, the client did agree that that wasn't going to be an issue once it was put into context how little this fourth corner pokes out. And more interestingly, the eventual fabricator contractor who was enclosed, but we didn't know that at the time, but they just decided that they would cold bend these panels into place. So you see the note at the bottom there, you see with a 1/2 inch offset over 20 feet, the warping when you do that is so little that you can just force it into place on site. So that's what they did. But we didn't know that at the time, but thankfully the client believed us when we said that this is not appreciable at the scale that it happens, which obviously saves a massive amount of money compared to fabricating these actually curved. Similarly, because there's a bunch of stuff, as you see on the right-hand side here, that needs to go between structure and skin, there's an offset that needs to be respected for where the slab edges occur. And we don't always set out slab edges. That's usually the primary structural engineer. I mean, we don't do that when we're not the primary structural engineer. In this case, we did because we had the control of the skin geometry, so it became logical for us to own that too. And now this slide is a little bit green, I think, but you can probably see how the sort of the arc nomenclature is defined in those arc composites along the kind of grid line system. And this actually, if you look at to the right here, the sort of the blow up of to the left, you see that the black line is the faceted actual skin, those metal panels, or in certain cases, glazing panels that you saw before. And then there's an offset. I believe it was something like 1 foot or 16 inches or whatnot. I don't quite remember, but it was defined by kind of how the curtain wall detailing worked and how it needed to be hooked into the slab. So that was offset back, and then actually, and this may or may not have been overkill, but it was sure fun. The rationalized so-called slab edge, according to my level 2 definition, is a composite arc shape where the individual arc radii and their tangencies are actually produced using using a genetic algorithm. More specifically, it was done using Galapagos in Grasshopper, because there are infinite amount of arcs that can be tangent to each other, and not necessarily the quote unquote best or fittest version of it. So we left that to the automation engine, and probably could have made our lives easier, but that seemed like a good idea at the time, and it worked out. And that became the slab edge setting out kind of mechanism. So here you see again the cladding, the rationalized contour, and then the slab edge. So the rationalization actually happens at the level of the skin, and then gets offset back. Okay, so going into documentation then,